Okay, so we have to learn how to do another gas law by the name of Charles' law. And the concept's pretty easy. If you have a sample of gas, say like a balloon of gas, right? And if it's at a low temperature, if it's cold, volume one, the gas is in a small balloon. If I could draw, it'd be great. So volume one and low temperature. And then if I heat that gas up, the balloon expands. We know that, gases expand when they get hotter. So we're going to see that same balloon get larger. The volume will expand. And we'll show you a couple classroom demonstrations of this, but that's a general concept. And that can be expressed in a simple equation. The volume over the initial volume over the initial temperature equals the final volume over the final temperature. Now, they did happen to rearrange this formula in a different way and I wouldn't even write it this way. I personally would have just said V1 T1 equals V2 T2. I don't need those times in there. But even that, I don't generally like. I will probably do all the solving in this form, where it kind of looks like a ratio and proportion. The only catch to using Charles' law is that temperature cannot be in Celsius. Temperature must be in Kelvin. So we have to convert all the temperatures. So it adds an extra step. And so what we're going to do is I'm going to do a couple examples of these. And I'm going to then set you guys off to finish up the rest of the problems. Let's do number 3. And the reason I'm doing number 3 is because it's got these little bars over the values in the temperature, which really doesn't mean anything. So I just want to show you those. So hydrogen gas is cooled from 150 Celsius, to 50 degrees Celsius. Now, again, there's these little itty bitty like lines over the numbers. Ignore those lines. That has something to do with something called significant figures, which we don't need to worry about, especially this old way of representing it. But I can't keep these temperatures this way. I do have to recognize that this is temperature 1 because it goes from 150 degrees Celsius to temperature 2. But I can't keep them this way. Temperature 1 is 150 degrees C. I need that Kelvin. And we need to realize that, I'll erase this for a second. Kelvin is equal to Celsius plus 273. So we need to have that in mind. So we have to convert. So temperature 1, which is in Kelvin, that's what we want it. We want it in Kelvin, is 150 plus 273. So temperature 1 is going to equal 423. Okay, and that is in Kelvin. Temperature 2, that's 50 plus 273, and that's going to equal 323 Kelvin. So we have to convert these. We have to convert it to Kelvin. We cannot keep them in Celsius. Otherwise, the formula isn't going to work. They have to be converted. Now, this problem's a little tricky because it says its new volume is 75 milliliters. So that new volume is V2. That's what they're telling you. V2 is 75. What was the original volume? So V1, we don't know. So let's write down our information. We are looking for, and the equation is, let's remind ourselves of the equation. V1 over T1 equals V2 over T2. That's Charles' law. And basically, again, this says if one aspect of this goes up, the other aspect goes up. If temperature goes up, the volume goes up. If the volume goes up, the temperature goes up. Had to have gone up, because that's the way a gas behaves. The hotter the gas is, the bigger the volume is going to be. The cooler a gas is, the more condensed and compacted and contracted it will be. So let's plug in what we know. Well, I'm looking for V1. That's what I'm looking for. Temperature 1. What happened there? Temperature 1 is 423. I have to use the Kelvin version. Volume 2 is 75, and I can use the milliliters. And 323 is the second temperature. Now, there's a bunch of different ways to solve this algebraically. I don't know what your algebra skills are. Typically, people cross-multiply this. It's probably one of the most common ways of doing it. And you solve for the velocity. You solve for the new volume. Let's see. So if I solve for the new volume, I get 98.2, which I'm just going to round to 98 milliliters. And again, if I used milliliters for my original volume, my new volume must be in the same units. Okay? And that's it. I mean, I say that's it. You got to convert temperatures first, which is a pain. That is true. And you have to make sure you put the right and interpret the problem right to know what variables are given and plug them in the right spot in the equation. We can do one more. I'll do number 8. No. I'll do number 6. I'll leave 8. 8's a little challenging. Not challenging. It's got its issue, but I'll see what you can do with that. Okay. But let's do number 6. So fluorine gas at 300 K. So, they already did they did the temperature for us. We don't have to make a new temperature. So we have 300 Kelvin, that's our temperature, occupies a volume of 500 milliliters. You know what, let me go back and wow, Tapper, come on. Let me go back. And so this is our T1, and this is our V1. They go together. At what temperature should it be lowered to bring it to a new volume? And again, those volume measurements do match. They're milliliters, so that's good. We need that to match. That's volume 2. And temperature 2 is what we're looking for. And so now we can go, V1 over T1 equals V2 over T2. And, if I want to write it all out, I just, use what I know. So I know volume is 500. Again, ignore the little bars over the numbers. That's an old school way of illustrating something, which we don't need to do. So 500 over 300 equals V2. I know is 300. T2 is what I'm looking for. You can cross multiply. 500 T2 equals 300 times 300. So T2 is going to equal 180. And this is in Kelvin. So whenever you get temperature, that will be a Kelvin degree. Or it's not a degree, it's just a Kelvin. Okay, and that's your answer. So you're going to try the rest. You're going to try the rest of them and turn it in by the end of the period. Okay? All right, thanks.